Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing the universe and developing new technologies that would benefit not only Thailand but the world society.
Hi, good afternoon, everyone, and good morning to the speaker. So, welcome to the IF Colloquium. Now, I would like to introduce our speaker for today, Dr. Siri Chongchitnan. He's finished his Ph.D. from the Institute of Astronomy in Theoretical Astrophysics from Cambridge. And now he is a reader in University of Warwick Mathematics Institute, and today he's going to talk about ExtremeValue Statistics in Cosmology.
Okay, thank you. Thank you, Tira, for the invitation, and I'm sorry for the delay. My computer probably wasn't cooperating. Can you hear me okay in the room? Yeah, okay, that's good. Okay, so I'm going to start sharing my slides. Okay, so today I'll be speaking about extreme value statistics in astrophysics. This is some work that I've done over the past few years, also some that I've done in collaboration with Tira, the host today. So we'll be sharing with you some of our work. Okay. So there are some questions that I'll try to answer today. So given an observational volume, such as the redshift range or the sky fraction, the fraction of the sky in which you're observing, what are the most massive Gasy clusters like? How big are they? Okay, what are the masses? And what are the most massive primordial black holes like? How big are they? How big are the largest cosmic voids? How big are the most massive population 3 stars? And how fast are the fastest spinning black holes spinning? If you don't have a background in astrophysics or cosmology, where if you're not sure what some of these objects are, don't worry, because I'll be giving you real quick facts. I'll be giving you quick facts about them as I go along. Okay, but the thing to note here is that the questions we are trying to answer are about really rare objects and extreme objects, hence all these most massive, largest, fastest kind of thing. Okay, so rare objects. Okay, so here's the overview of the talk. Extreme value theory gives us distribution or abundances of rare objects in a given observational volume or time period. So you've got to specify the object you're thinking of and also specify the volume, the observational volume, or how long you're observing, that kind of thing. Okay, and then the framework is going to give you something quantifiable about those rare objects. So what are these rare objects that I'm interested in today? I'll be giving you 3 different frameworks for extreme value theory. One is the exact extreme value theory, and I'll be talking about galaxy clusters, cosmic voids, and primordial black holes. There's also the block maxima approach. Again, I'll be applying this to galaxy clusters and the so-called population 3 stars. And finally, I'll be showing you the peak over threshold formalism, and I'll apply it to spin of primordial black holes. So just 3 different flavors of extreme value statistics. Okay, so what kind of background do you need? I think you need very basic kind of probability knowledge. If you know about a PDF, probability density function, and maybe the cumulative density function, just integrating the PDF. So basic kind of probability knowledge that will get you through my talk. Okay, so here's the general pipeline of the extreme value statistics, which I call EVS over here. The pipeline goes like this. Choose your volume in which you're observing, so some redshift range or some fraction of the sky, and choose the class of object you're interested in, such as black holes, galaxy clusters, whatever it is. Okay, and you probably want to have some kind of theoretical distribution for your object too. Theoretical, probably you have some kind of model in mind about how abundant something is, but you don't know what's the most likely abundant thing. You know, what's the most massive, most abundant kind of thing. But you just have the general kind of probability distribution for them. You put it into some kind of extreme value statistics framework, and I'll explain what that big green arrow is going to be. And out comes the extreme value statistics for your object. So it's going to be, the answer is going to be some probability distribution of your extreme objects. Okay, and the green arrow consists of whatever you like. One of these 3 frameworks, I'm going to show you the exact, the block maxima, and the peak over threshold. So we'll go over this framework for the different objects. Okay, so the first method is the exact approach, exact extreme value. As far as I can tell, the first time this appeared in Cosmology was in this paper back in 2011 by Harrison and Cole. They applied it to halo mass functions, and they derived the distribution for the most massive galaxy clusters. So that's my first object of the day, galaxy clusters. If you haven't seen galaxy clusters before, here it is, an example of a galaxy cluster. This is an image from the James Webb Telescope, and this was shown to President Biden in the White House, and there was a big press release about this back in 2022. And this is a cluster called SMAC 0723. This is at redshift of about 0.39. The mass is about 10 to the 14 solar masses. And you can see this image and it's basically every bright spot is a galaxy, right? And you can see a telltale sign of gravitational lensing. You can see that the galaxies are the galaxies are kind of stretched, right? They are kind of elongated, and it's going kind of around the bright spot. They're elongated. It tells you there's dark matter in between, and it's just light is coming to us bent, and it's coming to us in this weird shape. Anyway, there's a whole big clump of dark matter that you can't see, and this is what's kind of holding the group of galaxies together. The group of galaxies are behaving like a single gravitationally bound object. Typically, the mass of the cluster is 10 to 13, 10 to 16 would be the most massive one, solar masses, out to redshift 1-ish. Okay, so this image here of is a kind of not super high redshift at 0.39. The most massive objects of the universe, we believe, are galaxy clusters. Okay, so that's a super quick introduction to them. And the question we have in mind is we want a description of the most massive galaxy clusters in some volume. So we'll specify some observational volume. What's that like? Well, it could be something like a redshift range, maybe from minimum redshift to maximum redshift. And the sky fraction, you call that F sky, that goes from 0 to 1, 1 being the full sky is being observed. You've got some theoretical distribution of galaxy clusters in that volume. The typical way to do this is to specify something called the cluster mass function or halo mass function. If you've worked a little bit in this field, you might have come across something like Press-Schechter theory, Press-Schechter mass function. It tells you this dn/dm thing. N is the number density of your galaxy clusters. M is the mass of the cluster. So this is kind of telling you the differential density. Okay, so this is like a function. You don't really need to care what it looks like, but there's some equation, right, that expresses the NDM in terms of cosmological parameters and so on. So we feed this into our exact extreme value theory. I'm going to show you some equations on the next slide. What's the result? The result is this thing called the phi. Phi is the PDF, the probability density function of the maximum mass. Okay, so what is this pink arrow? What does that involve? What's exact extreme value statistics? Here's some really not very nice equations, but I'll just go through them quickly. So what you're looking for is some kind of measure of probability. If you take out a random galaxy, clusters from this volume, what's the probability that it's below mass m? Okay, so this is one of these factors. This capital F here is telling us about that probability. If you divide this capital F m by n tot, this is the second line, the third line. If you divide them up, you get a kind of a fraction. Yeah, a fraction which you can take as the probability. And that goes into one of these capital F. If you're taking out n samples from your volume, and you assume that they are independent samples, you then just multiply the probabilities together, and you get this f to the n here. And to get the PDF from the CDF, you just differentiate that thing. So differentiate f to the n. That gives you this last line here that tells you about the probability density function. If you didn't follow any of that, it doesn't matter at all. All you need to do is to look out for this kind of shape, in this kind of shape that looks like like this. Okay, so typical shape of the extreme value PDFs that you're going to get is kind of this, what would you call that? It's kind of asymmetric. It's positively skewed. It's got a long tail. It tends to lean onto the left with a long tail on the right. So this is a typical shape. You'll see this many times during this talk. This is a PDF for extreme value, for extreme Gasy cluster. I took this from that paper again, Harrison and Co. And this is happening in a, I think in a sphere of radius 100 megaparsec. And the curve that you get from the exact extreme value theory is in, I think it's the dashed line. So it's fitting well to some kind of simulation with the error bars. Okay, but we don't really need to dig into detail of what these curves are, but you can think about this as telling us about what's the most likely, most massive thing that you're going to see. Where the peak is kind of like a few times 10 to the 15, right? According to this graph, the peak is happening at maybe 2 times 10 to the 15. So you might say, okay, the most likely maximum cluster is going to be maybe 2 times 10 to the 15 solar masses. Okay, or you might say, oh, the peak isn't important, but maybe I need to quantify what's around the peak. So you might say, oh, it's we can form a little confidence interval around the peak, and we go, oh, the most likely extreme mass is between, I don't know, maybe like 1 to 3 times 10 to the 15 solar masses, something like that. Yeah, so it gives you some kind of confidence interval, and you can do that for whatever redshift. This is at redshift 0. You can do that for lots of redshift, and those slices are going to give you something like this, which is really nice. This is from the follow-up paper. I know this is a long time ago, 2011, but it's still quite relevant. Okay, so remember the peak of the PDF. This time, just think of every vertical cross-section as one of those peaks. Yeah. So this is telling us that these are the most likely extreme mass thing in as a function of redshift. So from this graph, you can probably say the most massive object in the universe is where the peak of this thing is kind of somewhere between, I don't know, maybe 0.2 to 0.3, right? That's where the most massive Gasy cluster is going to be. So this graph tells you that. And a nice thing about this graph also is that these data points are from observations, right? These stars are the data points that you get from various telescopes and space surveys. And if you change the cosmology a bit, if you say, okay, maybe my underlying cosmology isn't lambda CDM, is something else, then your prediction, this red kind of band, is going to change. So that gives us kind of a nice way to test cosmology using extreme objects. Yeah, so this is one nice application of extreme value theory. Okay, so that's Gasy clusters. My next object, again, staying with the exact extreme value, this is going to be cosmic voids next. Cosmic voids, what are they? They are just big regions in space of very low density compared to the average density. Is less than the average cosmic density, even though there isn't a precise definition of voids. That this hasn't stopped people from working on voids, myself included. I have worked on voids, even though we don't know what voids really are. Everyone's got some slightly different definition of what a cosmic void is, but generally it's things that look like this, like when you've got less density than the average. Okay, voids of radius about 100 megaparsecs are seen in simulations. And you think about it, that's a really huge area, huge volume in the universe that's essentially empty. It's not really empty, but it's low density. So, for example, in the SDSS Galaxy Survey, this is data release 12. This graph on the right here. It's now, it's a bit old. It's now data release 16 or 17, but still, this is very interesting that you can see there's um, there's cosmic voids up to radius of like 100 something, right? Over 100 megaparsecs. So we do see that kind of huge void in real galaxy surveys. Okay, so that's my quick introduction to cosmic voids. What do we want? Do we want some kind of probability distribution for the largest cosmic voids? Do we have some theory for that? Yes, we do. We have something like the Galaxy cluster mass function, but this time for voids. I know voids don't really have mass, but we still call it void mass function. It's just some description of voids. So in this case, you got dn dr, and is the number density of voids. Is the radius of the void, and there's some complicated function going on. It doesn't matter. It's just a theory that we have to describe how abundant voids are. This is one particular by Chef and van der Wegaard back in 2003. Okay, feed it through that machine, you get this again, this lopsided PDF of extreme voids. This is an example from taking my old paper. This is a particular PDF at redshift 0.225. I can't remember why I did that, probably fitting to some simulation. And the value of the void radius here, you can see here around 50 each, right? And you can put down where the 5th and 95th percentile are. You can't really do sigma because it's not normal. So you go, okay, 5th and 95th percentile around the peak. This is probably a good measure of how likely your maximum sized voids are. So 40 something to 50 something in this case. Okay. Right. And you can play the same redshift game. Let's do this for lots of redshift slices. And you see this kind of thing where you've got a band of prediction. The solid line is the peak, and the two dashed lines are just the 5th and 95th percentile of the most likely sized voids in given some theory, given that underlying theory. And you can see that it doesn't fit the crosses very well. The crosses are the SDSS voids that I dug up from the survey. Some way below, some are way above. And we shouldn't be really surprised because the theory is telling us about one kind of void, which is dark matter void. And the data, what you see isn't dark matter void. You can't see dark matter. You see galaxy void. It's just regions in space that don't have as many galaxies. So this kind of discrepancies in the definition of void is kind of hitting home at this point. You can't really compare them. So I guess the extreme value statistics is just telling us that you either need a better theory that describes galaxy void, or somehow the parameters aren't right, or something about the mismatch between the two kinds of voids. Okay. All right, so that's my object. I'll skip this slide. Okay, in the next object I have in mind is primordial black holes. So these are quick facts about primordial black holes. Primordial meaning they are not astrophysical black holes. They're not formed by collapsing stars at the end of their lives. It's just formed in the early universe during radiation era. Formed, I guess the quick way to say this is formed shortly after Big Bang, whatever that means, right? Formed in the early universe shortly after inflation, and they're just basically they have been there forever. They've been in our universe forever, and they've grown and they've accreted and they've become things like the supermassive black holes, SMBHs, at galaxy centers that we often see, and we think there's a supermassive black hole at the center of every galaxy. And they may also be the seed of the massive black holes that gravitational wave experiments like LIGO have reported. Those black holes need to be region of somewhere around 100 solar masses. Where are they from? Maybe they are primordial. Maybe they've just grown from some primordial seeds. Okay. And the last thing that people like to use primordial black holes for is dark matter. Maybe primordial black holes are dark matter. Who knows? And an interesting possibility is that all of dark matter might be primordial black holes. And at the moment, there's a small window. If you talk about primordial black holes, you can't avoid showing this plot. This is very busy plot, but it's just the various colors are experimental constraints. Okay, they're ruling out, so you're not allowed to be in that region if it's colored. The vertical axis is FPBH, meaning it's the ratio between stuff in primordial black holes to total dark matter. So for example, if F equals to 1, meaning the top horizontal line, it means all of dark matter is just primordial black holes. Okay. Meaning you don't need to go searching for exotic kind of dark matter at CERN. You just use primordial black holes as dark matter. And you can see there's only like a tiny window over here where it's kind of 10 to the minus 17 solar masses to 10 to the minus 11 solar masses. And the numbers are probably better in grams, maybe like 10 to the 15 to 10 to the 20 something, 23 grams. And people say that, okay, in this window, things are like the size of an asteroid. So people say, oh, an asteroid size primordial black holes, those are still allowed to be all of dark matter. Okay, so that's a nice review by Bernard Carr, who's probably the godfather of primordial black holes. Okay, in terms of extreme value theory, we want to know what's the most massive primordial black holes given some underlying theory. Do we have an underlying theory for primordial black hole abundances? We do, and it's very busy. All you need to care about is that here's the number density again and m here. So it's like mass function again, but for primordial black holes, the equations are very long. You've got little f here. Little f is defined in terms of this b, and it's a huge equation, which is not very pretty. And I refer to this paper to see more. But what we want in the end, shove this into the exact extreme value theory, you're going to get that lopsided PDF again. And here it is from an old paper, and Tira is also on this paper. This is, it doesn't look very lopsided, but it's not symmetric, right? It looks a bit symmetric, but it's not. It's that it has that kind of tilt again. And this is kind of telling us that, oh, if we make 10 observations, 100 observations, or 1,000 observations, what are the most likely mass of primordial black holes that you're going to see? And the PDFs are telling you just that at various redshift. Okay, and for example, this model predicts basically hundreds of solar masses. Okay, so that's primordial black holes done. And my next two methods that I haven't talked about, so moving away from the exact extreme value, these are entering in a kind of more classical extreme value theory that people use in other fields like engineering and meteorology, and predicting weather, predicting the kind of in other kind of engineering applications, you use extreme value statistics, and is one of these two types. One is called the block maximum approach, and the next one is the peak over threshold approach. So I'll go over this diagram a little bit more carefully over the next slides. But all you need to care about is that these two are like the central limit theorem in probability. They're just like central limit theorem. So we'll come and we'll go into detail in each of these methods. So method 2 is a block maxima approach. What is the block maxima approach like? Okay, I've got some cartoon to explain this. Question is, I want to find a distribution of extreme objects in this population. Okay, and this population, what I'm going to do first, I'm going to chop it up into lots of different blocks. And in each of these blocks, I'm going to take the maximum from each block. Let's say these are Gasy clusters. I'm going to chop them up into blocks of, I don't know, maybe this could be redshift bins. And then I could just take the maximum mass from each redshift bin. For example, if I have k bins, then that's that. Okay, and let's say if I have k blocks and each block contains n object, what's the distribution of this maxima like? Well, there's a theorem, the central limit theorem-like thing called Fisher-Tippett theorem. What does it say? It says that as your number of blocks increases and the number of things in each block increases as well, the extreme value distribution, the distribution of your x's, is going to be one of only 3 possible types. Okay, so it doesn't quite converge to 1, it converges to one of 3. And what are they? They are these 3 things called either the Gumball distribution, the Frechet distribution, or the Weibull distribution. And this is just a cartoon of what they might look like. It doesn't mean that the Weibull is tilted that way. It could tilt the other way too. It's just that it's one of these 3 types, and you can summarize the 3 types into one kind of distribution called the generalized extreme value distribution, or GEV. It looks like this. It looks like exponential of an exponential, basically. And if gamma is 0, it looks like this Gumball type. Okay, and here's Mr. Gumball. And when gamma is non-zero, if it's positive, is the Frechet type, and if it's negative, is the Weibull type. We call it Weibull, even though Frechet was the one who discovered this type as well. But here are the 3 types. Okay, it's basically depending on the sign of this gamma thing. Okay, so this is basically central limit theorem. Large number of blocks will give you one of these distribution. So we can apply that to Gasy clusters again. So this time I don't use the exact extreme value. This is a paper, Davis et al. They use the block maximum approach, and again they get this kind of lopsided probability distribution. This is the distribution of the biggest Gasy cluster in 100 megaparsec sphere. And they found that gamma is negative, which tells us it's a Weibull type distribution. Yeah. Oops, sorry. And it's a good fit to the data. And you can play the same game where you do the redshift slicing again and do PDF in each of these redshift slices. And this is done by my previous student, Tom Swallow, last year. And again, horizontal axis is redshift, and vertical axis, this is just telling us the most likely extreme mass cluster. And here the peak is along this line, and we've thrown in some data. These error bars, this data of error bars are just Gasy clusters in particular redshift, and it fits pretty well. There's some outlying Planck data here, but I don't think we've done enough correction to put it on this plot, but we put it in anyway. if you've done the correct kind of correction for bias, then it probably will fit that better, but we didn't have time to do it. Okay, so next class of object that we applied to this block maxima approach is population 3 stars. And here's some quick facts about population 3 stars for people who haven't heard about them before. The population 3 stars are the earliest population of stars. I know it's very funny to call something that came first as population 3, but that's how the naming goes. The youngest stars are on the population 1, and the oldest ones are population 3. And these are the earliest ones, and they are expected to be formed at redshift 10 to 20, and very massive, so hundreds to thousands of solar masses, so huge balls of hydrogen and helium, basically a very low metallicity, meaning there's basically no other kind of element involved. And when they die, and they don't live for very long, but when they die, they might explode into a supernova, or they might collapse into a black hole, or maybe they just continue as a regular kind of star. Okay, but that's a quick summary of population 3 stars. Can we use the same framework? We've got some underlying theory. We feed it into the block maxima approach. What do we get? You know what to expect by now. This is some new work led by Tira and myself and Joseph as co-authors. And this was out last month, so have a read. It's interesting. Okay, and this is the kind of shape again. This doesn't surprise you anymore, right? This is the lopsided shape, the PDF of the most massive population 3 stars. Again, it's the Weibull type, and it's this is for a particular choice of underlying PDF. You get peaks at about kind of thousands of solar masses. So in this model, for example, there's just lots of different curves here for different what you call star formation efficiency. The red one is what we fitted from a simulation. So for example, we can conclude that the most likely extreme population 3 stars is, in this case, 10 to the 3.7 solar masses in that particular redshift range of from 10 to 20, which is great because it's massive and it's kind of what you want. Okay, and you can do the same game for lots of various parameter combinations, but you get a huge range of possible peaks. These are just peak values. So ranges from 1 to kind of 4 something. That's a lot of possibilities. Okay, we'll skip that. Okay, here's the last method of modeling extreme values called the peak over threshold method. So let's explain this with a cartoon. Peak over threshold method starts with your PDF, again, your underlying theory. And you want to know about how rare something happens at the tail of the PDF. So you put a threshold U there at the tail. So for example, this could be, how if this were, say, temperature distribution in the year, you might ask, okay, how likely is the temperature going to exceed like crazy hot here over the next 1 week period? Okay, so might be, or something like, it could be how likely is the water level going to increase beyond some crazy high level that doesn't normally happen if you want to predict floods, for example. Okay, so this threshold U is some kind of really high thing that you don't expect to happen, and you want to know what happens beyond this, basically. Okay, how rare does that happen? You want to quantify the tail of the PDF. And down the tail of the PDF, you can quantify the tail by asking about the probability that your observable exceeds your threshold. So the observable is capital X greater than U. What's the probability of that happening? You call this little x. Little x is just how far does it go into the tail. Yeah, so x is greater than U. How much further does it go in? So that's called the exceedance. Little x is called the exceedance. And you can form this kind of new probability distribution that's formed by this fraction here on the right. So the capital F is my CDF, right? The cumulative probability. So you can see that for this fraction, if let's say if x is 0, meaning it doesn't exceed U, if x is 0, then this right hand side is completely 0, right? And as x goes to infinity, if it exceeds a lot, then this capital F is going to be 1. So it's 1 minus F over 1 minus F that gives you 1. So this fraction is like a measure, an estimator of some kind of probability that goes from 0 to 1. Okay, right. So you call this F sub U. The excess distribution is quantifying something about the tail. You basically throw away everything that comes below you. You throw it away and just basically model the tail. Modeling the tail, you can do it with this excess distribution. Okay, it's a CDF. And that's a theorem that's like the central limit theorem that's got to do with this tail called the Picans-Baukema-de Haan theorem, very long name. And this tells you that when the threshold, if you set this vertical bar to be very high, down the extreme tail of this thing, so extremely rare events, then this excess probability, excess distribution will converge to a particular type of distribution called the generalized Pareto distribution. How does the Pareto distribution look like? It looks like this. Okay. So again, this is just a cartoon, but basically it's between 0, going from 0 to 1. And it looks like 1 minus exponential, basically. Yep. So generalized Pareto distribution. And you've got kind of one of 3 types, almost like positive or negative psi or 0 psi. And this is again like central limit theorem. Okay, so you can almost say that this says that the tail of probability distributions, they look similar, right? Regardless of the distribution, the tail kind of looks similar. And I'll show you a result that we applied this peak over threshold formalism to. This is spin of primordial black holes. And the spin of primordial black holes, if you know a little bit about GR, you might recall something like the no-hair theorem, right? The black hole no-hair theorem, which says that black holes only have 3 attributes: the mass, the charge, and the angular momentum. Angular momentum being J here. And you can measure this quantity, Cj over Gm squared, and you call this little a, and that's just a spin of a primordial black hole. So what are these things like? Quick facts about spins of primordial black holes. A ranges from 0 to 1. If it's 0, it's not spinning, it has 0 angular momentum. and the highest it can be is 1. So A of 0.7, that's kind of a typical spin for supermassive black holes. A of 0.8 to 0.9, that's kind of a high value for massive black holes, like things that are formed by binary black holes, yeah, from binary stars. And then you've got a 0.998. This is a famous limit called the Thorne limit, which is believed to be the absolute maximum for astrophysical black holes. If black holes are formed from astrophysical events, collapsing stars, then it would never spin more than 0.998. A of 1 and above is prohibited because the more the black hole spin, the more it reveals the singularity, the more it loses. This event horizon thing shrinks, and when A goes to 1, it becomes a naked singularity, and Hawking's cosmic censorship doesn't allow that to happen. So it can go really close to 1, but it can't be 1, basically. Right? So another interesting fact is that if black holes are spinning really fast, they become stable against perturbations, and against even Hawking evaporations are stabilized against that. It won't evaporate as much, or may not evaporate at all if it's spinning quickly. Okay, so and if that happens, then maybe we can use even more primordial black holes as dark matter candidates, because they don't tend to go away. They tend to stay as they are. It's good to have spinning black holes, basically, if you want dark matter. Okay, so you feed this into the pot formalism, the peak over threshold formalism, and you get this excess CDF thing that I was talking about. Remember, the thing that goes from 0 to 1, and you get all of these curves from different thresholds. So U of 0.9, 0.8, and 0.7, for example. And these are curves that you get from that theorem, right? From saying that, oh, down the tail it converges to something, and then you fit that parameter. You can't really do it with the actual PDF, because when you exceed the parameter that much, computationally it doesn't work anymore. Like your computer will go crazy. You can't deal with that small number. But if you use that theorem, use the Balkena-Dehaene theorem, then yes, you can model the tail very far away. Okay, and that gives you a nice method to probe the tail. What's this gonna do? Well, from this you can derive something called the return levels, and this is a very interesting quantity. Once you get the excess CDF, you can use it to calculate this thing called return levels, which is just asking, okay, how many observations do I need before I exceed that threshold? So, for example, in the top graph here, the return level is set between 0.8 to 1. So for example, 0.8, you're asking, okay, how many observations of black holes do I need for the spin to exceed 0.8? And if you read this, it's about, I don't know, a couple of hundreds, right? 10 to the 2. So it's saying, okay, every 100 or so black holes, I will have one in which the spin exceeds 0.8. Okay, and you can do that game for some crazy values of the spin as well. If you zoom into this really top level here near 1 and zoom in, you get this lower graph, which is zooming in the return level between the Thorne limit 0.998 to 1. Of course, you're not going to get 1, but you're asking something like how many primordial black holes would have spin that exceed 0.998, and the answer tends to be kind of millions. Okay, so it's saying that Thorne limit is exceeded once in every million black holes, for example, and that's nice because we know that astrophysical black holes can't exceed the Thorne limit, but primordial black holes can. So this tells us that there are probably black holes out there that exceed the Thorne limit for the spin. Okay, and that comes from a nice application of extreme value theory. I'm going to conclude now, just staying on time. The conclusions are that I've shown you that extreme value theory gives us a distribution and abundances of rare objects. And those rare objects are the astrophysical objects that I talked about. And I described three frameworks, three formalisms, the exact, the block maxima, the peak over threshold. And remember, the block maxima and the peak over threshold, they are just basically central limit theorem. We have applied it to these kind of rare objects, massive Gasy clusters, the largest cosmic voids, the biggest primordial black holes, the most quickly spinning ones, and the biggest population 3 stars. And what can we learn? We learn that they can be a test of cosmology or structure formation. Okay, the rare clusters and voids, or in the case of primordial black holes and population 3 stars, they could be dark matter. They could give, these rare objects should give us the origin of dark matter and supermassive black holes. So, yep, that's the end of my talk. Thank you.
Anyone in this room has a questions? Anyone? No. Okay. I actually have a questions about the mismatch between the size of the void from galaxies and then the void from dark matter. Do you think that it is possible to introduce the bias just the same way as we did with the cluster of galaxy, and then we could be able to recover the inconsistencies in the plot?
Yeah, probably, but I don't think that's enough. I think it's basically two different definitions of things. Yeah, it might be. Yeah, there's probably some kind of bias happening. Yeah, that voids can cluster and they can join up, but I think that's not enough to solve the problem. I think it's just a matter of coming up with a consistent definition of what a void is, like setting what delta is supposed to be and what the boundary shape is like. Otherwise, yeah, we're just talking about apples and pears and comparing results. Yeah.
Okay, and I have another questions about is there like any like minimum volume size that your extreme value statistic will work? Like if it's below that volume, there will be some inhomogeneities that will break down your statistics.
Minimum volume size. Yeah. I guess the problem is if you go too small, you might not find enough extreme stuff. Yeah, because theoretically that isn't like a limit, but in practice, you don't want the volume to be too small because you don't find enough extreme things, and you want the volume to be too big either because then you don't have enough to reach the large n limit. So it's like in practice is a balance between not too big a volume and not too small a volume, so that the theorem apply and you also find enough extreme things.
Okay.
First of all, I'm not in this field, so it would be a naive question. So I just have a question about one of your slide about the formula of A equal to something like J over the M square.
Yeah.
I think about the spin of black hole, I guess.
This one, yeah.
Yes. In like particle physics, we have the similar kind of relation that if we measure the spin of the particle and measure the mass square of the particle, and if we map all of the like all of the observed particles, it's linear. It's linear as like if you plot like the m square and the plotted spin of the particle, it forms the linear trends. I don't know if it's related or not. It just remind me of that. At the A, something is called the ledge trajectory or the ledge slope of that is
Okay.
it's a
So you
constant.
okay. So you're saying that A and M has a they have a linear relationship?
It's what I say that in particle physics, the spin of the particle and the mass square of the particle have relation. It's a linear relation of. It's a linear relation.
Okay.
Exactly.
I think are we talking about the same spin though? Because I guess in particle physics, the spin doesn't really have to do with rotation per se. Is that right? Yeah. So the elementary particle spin is probably not the kind of spin that I'm talking about here. Here we're just talking basically angular momentum, whereas for particle physics, spin is like a quantum number, which is not we're not doing a quantum number here. I don't know. Does that make sense to you? Like we're probably talking about two kinds of spins.
Yeah, maybe I'm not quite probe your question, but I'm just state out of my curiosity that it remind me of that relation.
Yeah. Yeah, I think that's it. I think we're talking about different definition for spin. That's my guess. Where I'm talking about the angular momentum. Yeah.
Okay. But the I to be honest, I don't know what exactly A is.
Okay.
What the A on the left hand side is.
It is basically angular momentum divided by mass squared.
Okay.
That's all. Yeah.
Okay.
Okay. I guess there isn't any questions, right? Let's thank for the speaker again.
Thank you. Thank you for listening. Thank you.
มันต้องทำอะไรอีกไหม ขอบคุณครับ
Okay. Shall I go? Okay. Thank you ครับ